Another type of interference and diffraction we can look at are circular apertures. Everything we've been looking up until now have been lines, or what we called slits. So something that is effectively simplifying down to a one-dimensional problem because we have one dimension that just extends out symmetrically. So once we start looking at circular apertures, it's a little harder for us to see the picture here. This is a side view. So this actually looks just like, for instance, the single slit diffraction scenario. However, instead of it being just really, really long in the direction coming towards us, there's a rotational symmetry. So actually, you do get a different pattern here. If you compare this to the one-dimensional slit scenario, or the single slit diffraction experiment, we do have a slightly different pattern to where our dark locations are and the relative intensities. Now, similarly, you're going to notice that what we've indexed are the dark spots. So to actually do this analysis out, you would do it the same way we did the single slit diffraction of thinking about pairs of points and thinking then about dark spots. However, in this case, it has to be rotationally symmetric. The book simply gives you the answer here. This is one of the very few times in calculus-based physics we have to say that the derivation here is beyond the scope of the class. And so instead, we are going to simply give you the answer and not tell you how we derived it. But it's important to recognize that this is actually a circular hole, and we would get these circular fringes. So the location of the first dark fringe is given by this. This 1.22 number is not exact. It's just the 3 sig fig number that is coming from the advanced derivation of this. And so this is the angle at which you have it. So it's lambda is the wavelength of whatever light you're looking at over d, which is the diameter of the opening. So effectively what we're doing is figuring out this angle, which takes us to the first dark band. And again, you can see that this is kind of like taking our single slit diffraction pattern and rotating it around, though not exactly. So that not exactly part is where this 1.22 comes from. So that's important. The width of the circular maximum is just saying, well, I have this big circle here, what's the width? Now the work here is really the same as the single slit case where you just take the distance and multiply it by 2, where it's L tan theta, so again given by this. And this approximation here is saying that we're going to approximate tangent of theta to be equal to theta. So that's our small angle approximation. We can do it as long as theta is in radians and as long as theta is very small. So basically, because theta 1 is given by this, we plug this in here, and now you get that the width is given by lambda L, where L is the distance between your aperture and the screen, and D, which was the diameter of your aperture. So this is pretty reasonable to use most of the time. These angles are pretty small, similar to how our single slit diffraction angles were small. So again, that will give you the width, which is basically the diameter of this circle. So, okay, what's the point of talking about this if we can't actually do the derivation? There's actually a number of applications. So one that the book mentions is sound going through a speaker opening. And one thing to be careful about with sound is that frequently our small angle approximation no longer applies to sound. Sometimes the relative scale of our apertures and our wavelength and our distances make it so that you don't want to use the small angle approximation for sound. But if you're generating sound within a speaker based on the membrane going back and forth, it maybe has to pass through a speaker cone or whatever hole you have in the speaker. And so that itself is diffraction as it goes forward and then spreads out. Now, interestingly, there's a number of places where this occurs naturally for light. So if you think about telescopes and microscopes, there are lenses. Now, in some cases, these lenses are very, very big. But in other cases, you might have apertures or small lenses. And the reason for that would be blocking external light. So only taking the centrally focused light, passing it through, for instance, an iris, and then onto the rest of your optical components. So in that case, for light, if you're trying to use small enough apertures or small enough lenses, you actually do start to run into diffraction limits. And in that case, these would all be, of course, circular. Lastly, and kind of related to the previous one, is that fundamentally our imaging resolution is limited by diffraction. So if, for instance, you want to take a microscope and look at something really, really small, again, when you start thinking about the lenses, you need to start blocking out outside light. So if you want to focus down to something that is, say, only a few microns in scale, you might start putting in apertures that are also a few microns or uh, maybe fractions of millimeters. So our fundamental limit to imaging resolution, basically how small can we see stuff, actually comes from this diffraction limit. So if you want to make a really, really accurate microscope, you would need to start thinking about these. And so you might see some of these applications in the calculations, but especially for those of you who are interested in the biological science or might do some sort of optics work in chemistry, at a certain point you have to actually consider this diffraction limit, especially with apertures and focusing things. So that's pretty cool. And again, we don't do the derivation here because the math gets really, really complicated, but you can just kind of use these equations and work with these as long as you understand what they represent.